I'm a bit not so well prepared as usual. The reason is basically because I will be talking about very recent work, which is still work in progress, so it's not finished. And I will show you some intermediate results, and because I thought not so many of you are working in this field, I switched a bit the subject just to make it more general. So the title is more general, from form factor series for dynamical correlation functions of the XXZ chain. Before it's said in the antiferromagnetic massive regime, I will talk about that, but I will also talk about the general picture and some more. I'll give you some extended introduction to give you the context. So the outline of the talk is as follows. I'm giving you some information what are dynamical two-point functions of quantum chains. I think not everybody is working on many-body quantum systems, so I should repeat that, and this is also useful in order to explain the notation. Then I'll explain so what is our specialty in this field. It is called the quantum transfer matrix formalism. This is some specific way of dealing with finite temperature, so of constructing the canonical density matrix of an integrable system. Actually of any system, but for integrable systems it can be done in a way that this new object, the quantum transfer matrix, is also an integrable object, something which can be diagonalized using integrability techniques. Then I'll introduce to you what we call the thermal form factor series for transfers, the thermal form factor series for dynamical two-point functions first. It is a form factor series where we use the basis of the eigenbasis of this quantum transfer matrix, not the eigenbasis of the Hamiltonian or the usual transfer matrix. And this gives you series representations which have very nice properties, in many cases better properties than usual form factor series, and I'll try to explain you what I mean by this. The example, this is what I now pressed into this talk, which I originally didn't want to talk about. So the example would be the transverse dynamical two-point functions of the XX chain. This is also recent work published this year, so it's not so old, and maybe it's worth talking about it. And this is probably a very good example for you to understand the general problems and general aims of our research. Then I'll talk about this new thing, which is thermal form factor series for the longitudinal dynamical two-point functions of the XXZ chain in the loading limit and in the massive regime. And then I summarize. So that will be a lot of stuff, and I'm not sure if I can tell you all of that, so we have probably time to time we have to jump. So since I'm giving you an overview, this includes some older work of the last 5 years, and I'll be explicitly referring to some work with my former student Maxime Degaff, and also work which was done with my colleagues at Wuppertal, Karbach and Klumper, but always the collaborators are always, which are always in these works, are my main collaborators, Karol Kozlowski and Junji Suzuki. Karol Kozlowski from the ENS de Lyon, and Suzuki is from Shizuoka University. And for the new part, so the very latest part, we have a new collaborator who's in the audience. It's Konstantin Babek, who's at the moment a postdoc at Wuppertal. So the history of the problem of the interesting new part about the massive regime of the XXZ chain, of course it's long, but here I list the main works, in my understanding. The main contribution here there are two sources. One is the Vertex operator approach. So Jimbo Miwa in their booklet, which appeared as an American Mathematical Society booklet, they give formula for form factors of local operators of the XXZ chain, so the sigma z Pauli matrix, or sigma plus and sigma minus operators. They give expressions for that, and those expressions are given in terms of multiple integrals or multiple residues. it's rather complicated stuff. So multiple residues, and they give only a description of the contour. The contour is such that this and those poles are inside, others are outside, and it's a multiple integral. It has a nice physical interpretation in terms of so-called spinons. Spinons are the excitations of the spin chain, of the XXZ chain, and this series is graded by the number of excitations. So there's a first term, which may be 0 or non-zero, just a number, and then comes a 2-spinon contribution, a 4-spinon, 6-spinon contributions, and they are represented by 2-fold integrals, 4-fold integrals, 6-fold integrals, and in the integrands, the functions in the integrands are again multiple integrals. Those form factors. And so what the new feature will be that the function, we will still have this series of multiple integrals, 1 plus 2 plus 4 plus 6, and so on. But the integrals in our new result will be simple, explicit, beautiful functions, classical functions from the 19th century. Okay? But the first important work was this Jimbo-Mira work, where they have multiple integrals, but for the 2-spinon case, they have also an explicit formula for the plus-minus form factors. Plus-minus. And this was another explicit formula for the 2-spinon form factor was found by Michal Lashkiewicz, who got it actually from considering the XYZ models in the vertex operator approach. So explicit formula were known for the 2-spinon contributions to the series. For the higher spinon contributions, only multiple integrals. And this is about the vertex operator approach, an approach where the analysis is done on the infinite chain. And it is done using representation theory of affine quantum groups. Things like, which were developed by Lukyanov, things like vertex operators on the lattice and bosonization of lattice vertex operators. These are the techniques. And there is a completely different set of techniques for calculating form factors, which was, for the XXZ chain, it was pioneered and I would say, well, there were works before on the linear model and so on, but I think the structure of this was clearly understood, and the pioneering work is here, this work mentioned by Kitani, Mayer, and Terrasse in 1999. This is for finite chains, so they take a finite chain and calculate form factors in terms of beta roots. So they are parameterized by beta roots, some parameters which are solutions of complicated nonlinear equations. So this is the second story, beta-ansatz approach to form factors. And here the problem is then to do the thermodynamic limit. I mean, the number of beta roots goes to infinity and so on. And this took 10 years to get this under control for the usual Dot-Semantics, and it only, well, it was only, say, partially under control, I would say, for the in the massive regime. So in the massive regime, this limit was done in a paper, in this paper, which I'm citing here. It's a joint paper with my student Maxime and Karol and Kyunji. So the thermodynamic limit of these beta-ansatz form factors in the massive regime for the usual Dot-Semantics was only done in 2015. I think I talked about this in one of the darkest meetings. But then there is this new approach, different approach, that instead of using form factors of the usual Dot-Semantics, one can use form factors of the quantum Dot-Semantics, and this gives different series. So this is in these other groups which are cited there. From the 2-spinon form factors, this explicit formula, there are very nice results which are very important in applications. First, I think just say really useful exploration into that was from my Wuppertal colleagues, Skarbach, Müller. Müller is from Long Island, from Rhode Island, Musik is at Montreal, but Flanderjan, Müller, Skarbach, colleagues from Wuppertal. This was later extended, so this is on the XXZ model, and in this paper by Jean-Sebastian Coe and his student Rob Hagemans, they extended this to the four-spinor case. So they used this multiple residue formula for the four-spinor case. And what they did the Fourier transformation in space and time, and then you can compare with experiments. And I think many of you saw these color-coded pictures where people compare Heisenberg correlation functions with neutron scattering experiments. Those are those works. Okay, so this is the history for me. So we have to keep in mind there are two approaches. One is the vertex operator approach, and the other one is the beta-ansatz approach. And now a third one is the beta-ansatz approach applied to the quantum transformatics. And all of those give you different expressions for the form factors and series. Okay, so I talked already a lot. Many slides to go. But I think it's important to give you the general picture. Maybe you can speed up now a little bit. So this is the introductory picture for people who don't work in lattice models. I'm usually considering a quantum change. So the interesting thing here is that I have a finite Hilbert space, which is composed of a finite dimensional local space, and copies of it as the length of my chain, and I take the tensor product, H as the Hamiltonian, and it's a finite matrix, so everything is regular here. The local operators are those which take on one lattice side, for instance. There maybe as a concept of local operators. So the advantage of this is it's pretty wide. If you send L to infinity and let the Hamiltonian parametrically depend on L, you can also realize quantum field theories this way. And so I'm doing quantum statistical mechanics. Quantum means I'm using Heisenberg time evolution. This is important. And statistical mechanics means that we calculating correlation functions by doing averages with density matrix. The density matrix, the basic one, in my understanding, is the canonical density matrix, the density matrix of the canonical ensemble, Gibbs ensemble. But nowadays people are interested in non-equilibrium, and then different density matrices occur. So if you have a density matrix, in my case the canonical one, and time evolution, then you can calculate objects or define objects like two-point functions. x1, operator x, acting at side 1, operator y at side m plus 1, so m is the distance between the sides, and you evolve the operator at side m plus 1 in time, and take the canonical average, and then you want to do this in the thermodynamic limit where the system size goes to infinity. The latter is important because it simplifies things. Okay, so this is what we want to know in quantum statistical mechanics, and the nice thing is that there is some very general background here. It's called linear response theory or Kubo theory, and this connects very generally the response of a large quantum system to time-dependent perturbations. An experiment is a time-dependent perturbation, so it explains how experiments are described by dynamical correlation functions at finite temperature. Those are the usual conditions for experiments. Temperature is always finite, and correlation functions in most interesting experiments are dynamical. So in neutron scattering, you have dynamical correlation functions. In ESR experiments, you have dynamical correlation. This is what we want to know, and since we are mathematical physicists, we would like to calculate it, and then if you try it, you quickly find that it's not so easy, and I'm looking for a particularly simple model, one which is particularly simple in my understanding, and but still interacting in the sense that the S matrix of the elementary excitations is non-trivial, is this XXZ model. Here the Hilbert, local Hilbert space is C2, so it's just spin up or spin down. And the interactions, the Heisenberg interaction, which may be deformed a little bit by this anisotropy delta. The last term is the magnetic field which couples to the chain. So the main goal of my research for many years is to calculate such two-point functions, dynamical and at finite temperature. And And I want to know this function for all values of distance of the spins, for all times, for all temperatures, low and high, and for all values of the magnetic field. The depressing message is that we don't know anything basically about these objects. I mean, in the sense of mathematics. So there are some numerical simulations and so on. But so the way I'd like to know it as a mathematical physicist, in this respect we don't know so much. But an exception is this case when delta is equal to 0. This is called the XX chain. For the XX chain, the system is simpler, so the spectrum, if you do a Göhmann transformation, this becomes a model of free fermions, so the spectrum is equivalent to a spectrum of free fermions. And so this is probably the reason behind the simplifications. Yeah. So there something is known. But for instance, even for the XX model, what was known, say, for a longer time, are the 2-point longitudinal functions when the operator is sigma z. If you change this operator to sigma x, much less is known, and only in our very recent work, which I'm going to talk about, we got some progress. I can tell you what was known before, and I'll tell you what the progress is. A lot was known before, and the progress is, in a sense, small, but not everything was known. But here, for this XX model and the longitudinal correlation function, sigma z, you have a very simple and nice answer. So just the product of two integrals. And the two integrals are kind of wave transforms of the Fermi waves. Fermi wave for holes and particles, and the product of those. Those give you the correlation functions for the longitudinal SD correlation function of the XX chain. And this is very simple, but so you can plot it. I did that for you. The black line is the plot of the integrals, just numerical plot of the integrals, and the blue dots and the red dots are what you get from a subtle point approximation to the integrals. I'm showing you this picture for two reasons. First reason is I want to show you what correlation functions, dynamical correlation functions are, how they look like, and they always look like this. This is typical behavior of a dynamical correlation function. So what you do is you perturb your system at some point, then you sit at some other point where you measure, you wait for a time, and the perturbation will spread, and at some time later, depending on the interaction, there's some natural speed of propagation of this perturbation, you will find the perturbation. It's like you throw a stone into the water, and some of your friend is sitting in a boat far away, and then you will create a big wave. The big wave will come to the boat will go up, and then there will be many small ripples behind the big wave. This is a quantum signal. This is what happens in measurements. So, and they all look like that, but the representations are not always as simple. It's not always double integral, product of two integrals, maybe something much more complicated. I showed you the center point approximation here because this is what we usually want to do. We are interested in asymptotic analysis. So this is particularly what my collaborator Karol Kozlowski likes. We want to analyze the series we get asymptotically, and here this is to convince you that such a thing is very efficient. Subtle point approximations, asymptotic analysis is something which gives you simple expression for some complicated dynamics. Okay, so this is the, now I tell you about this quantum transsemantics. Quantum transsemantics, well, I hope you're familiar with the graphical notation for vertex models. So here we have many vertices, so every cross of lines is an R matrix. And the usual transsemantics of the 6-vertex model, the usual transsemantics, all the arrows would point in the same direction. And here we have an object where they alternate. That is the only difference. So what is it good for? If you have the transsemantics of the 6-vertex model, and you diagonalize it, it gives you the partition function of the 6 vertex model, not the partition function of the spin chain. So if you take the derivative at the logarithmic derivative at 0, you get the Hamiltonian of the spin chain, while this formalism gives you ground state properties of the Hamiltonian. It gives you, from the usual transformations, you get finite temperature properties of the 6 vertex model and ground state properties of the XXZ model. If you want to have finite temperature properties of the XXZ model, you have to look at this object, this stated form, which is called the quantum transformatics, because it gives you is a transformatics for which gives you the partition functions for the quantum object. The quantum model is the spin chain, the classical model is the vertex. Well, the terminology is a bit strange, I think, but it's some traditions are used.
But so do you really fix the spins?
Yes, for here I fixed the spins. You mean the representations?
No.
No.
I mean, you said spin up, spin down, spin up.
No,
it's not a matrix.
No, this is, no. This is right. You have to, it's just a matrix.
Yeah.
This is just representing a 2 to the n matrix. 2 to the n by 2 to the n. I don't fix the spins. So the arrows is just, right. So the point is, if you diagonalize the thing, then it has a rather strange spectrum, even if the model is critical. The transfer matrix, the quantum transfer matrix, has a gap spectrum, and it has always one eigenvalue which is largest in modulus. It's never degenerate. So there is an eigenvalue which we call the dominant eigenvalue, and it has the property, or the dominant eigenvalue determines the free energy per lattice side. So the free energy per lattice side of the quantum transfer matrix is minus temperature times logarithm of this dominant eigenvalue. So in all the thermodynamics of integrable models, fundamental models, where both space dimensions are the same, like Hubbard or TJ, or whatever you may think of, all the thermodynamics of all of these models is determined by a single eigenvalue of the quantum transfer matrix. That's why it is good. If you are in the usual formalism, you have to sum over all eigenvalues, you get all the strings and all the stuff, TBA. This is avoided here. So in the beginning, this was also called thermodynamics without strings. And so this is old story. But I came into this, I entered this game with this paper in 2004. The observation was that, well, one eigenvalue determines the thermodynamics. And my observation was that the corresponding eigenvector, the dominant eigenvector, determines all static correlation functions, namely, it determines the reduced density matrix. So the density matrix of the finite system is this, e to the minus h over t normalized. But this doesn't have a limit when n goes to infinity. It's mathematically not a good object. But if you trace out everything but the finite piece, then you the limit, and it always exists. And this, by an inductive limit, also allows you to define, say, correlation functions on the infinite chain. This is a point of view which was put forward by my friends Rost, Jimbo, Love, Takayama. And we heard a lot about this 10 years ago. So this is the reduced density matrix, and it is determined by a single dominant eigenvector. And we want to calculate 2-point functions, static 2-point functions at the moment. What we can do is, well, you see, you take this formula. This is the reduced density matrix. So in order to calculate expectation value, you multiply with the operators and then trace. And you get this trace, and in the middle, the trace of this object is the quantum transfer matrix to some power. This is not such a nice object to analyze because of this power here in the middle. And so in this, say, for the XXZ chain, this is a trace of this monodromy matrix, so it's something like a plus d to some power. If you expand it, you get exponentially valued terms. When m becomes large, it's maybe not so good for large distances. This is good for short distances. For large distances, what you can do is you can insert a 1 here, so you can expand in the basis of eigenfunctions of the quantum transfer matrix. I call these eigenfunctions psi n here, so you expand in the basis of psi n. The psi n's are those ones are left eigenvectors of the quantum transfer matrix, so you get the eigenvalue to the power m minus 1. So I could use it as minus 1. So this is what I call the summary form factor series. It's something very simple, or it's hard to analyze. The hard thing is here is to do these limits, n to infinity, and so on. And we started doing that with my student Maxime and with Carol in 2013. Actually, after Lucky's meeting, I met Carol. It was, I think, in Angers. And we talked about this. And it turned out that we both started working on it, and we both had already some files, so we showed each other our results. And then decided to do this together. So Lucky's was very useful for this collaboration. It initiated our collaboration. Okay, so then, how, I'm still in this extended introduction, so this can be extended to the dynamical case. So here's the graphical representation of a dynamical, of a discretization, or a total discretization of a dynamical correlation function. So this lower part, so here are my two operators, y and x. The lower part, the part below x, here is a representation of the operator e to the plus or minus, I forgot, ith. So it's part of this Heisenberg time evolution, and the other part comes from upstairs, and with the 1 over t, is the temperature. It also includes the density matrix without normalization by the partition function. So this is the representation, and what I did here, I introduced these two lines, minus epsilon and epsilon, which move the points. So if you send epsilon to 0, they will annihilate each other, and the gray point will be on this line here. This is called the solution of the inverse problems, a famous trick of the Göhmann. If you do that, this gray point is here, and the transfer matrices themselves at certain points are inhomogeneous shift operators. If you apply them n over 2 times, you will shift this gray point here, but you have n over 2 more lines here and n over 2 more lines here. Okay? Well, then it looks as before. Unfortunately, you have n over 2 lines and you want to set n to infinity. This cannot be done. But if you then insert this complete set of functions, then you get something which gives you a limit. I'll show you in a minute. So here's the theorem from this paper. So take any fundamental integral lattice model, which is one symmetric R matrix. So there's some conserved quantity which corresponds to the magnetic field. So the SC, total SC in the XXZ chain, and alpha is something like the magnetic field. Then there is the staggered matrix, the one from the previous picture. This was the pictorial representation of this object. This is the associated staggered inhomogeneous monotony matrix. We call the trace of this in series space A. The inhomogeneous quantum transfer matrix, whose eigenvalue we denote by capital lambda n, the eigenstates by psi n, and then we introduce the same notation as before. So x, capital X and Y are the traces of local operators with this staggered monotone matrix. Then theorem says there exists a total decomposition. The one I've shown you on the previous page, for instance, is not unique. There exist many. But the one on the previous page, for instance, allows you to write the two-point function in this way. So all these additional lines, they just give you eigenvalues to some power. And this combination here, because also the argument of the eigenvalues depends on n, has a limit. See, if n is infinity, this is 0, this cancels, this is 1. So this goes to 1, and it's just something like the Euler formula. So you see that this has a limit. And so this is a nice representation. And we're playing with this for a while. And it's nice, but it's hard to analyze still. doing this for 3 years or so, with several examples. And what you have to do is you have to evaluate the non-vanishing amplitudes. Many of them are 0 because of some selection rules, spin conservation, things like that, but there's some infinitely many typically non-vanishing amplitudes. You have to evaluate them, then the eigenvalue ratios, then sum up the series, that's all. And do the limit to infinity. Okay. So there are some remarks. Summation and total limit do not commute, so you have to be careful with the summation. There are some nasty points, but they can be generally solved. So it's just something you have to be careful with, but it's not a problem. It's not a problem which remains. It was just a problem when I did it the first time, because I made a mistake there, which was pointed out to me by Julie. So, but it can be healed, but you have to be careful. If you set time to 0, you recover the static case. And as I said, there are some selection rules, and there's a very special case in the XX chain, the longitudinal case, the simple case I showed you before. There is kind of super selection. Selection rule says, in that case, that only one particle, one hole excitations have non-vanishing amplitudes. This is why you have only two integrals. It's not a question of the spectrum. It doesn't have to do with the free Fermi spectrum, but with the kind of super selection rule for the amplitudes. And if you look now, we now look at the transverse case, there is no such super selection rules, and you have infinitely many. So you have one particle, one hole, two particle, two holes, three, four, and so on. Let me describe you, now it will become hard, when the formula will be on here, but I don't know if it's possible to follow. I'll try to give you the flavor of it. So we will see all these. I mean, let's go back first. So this is the most simple case. So here is the most simple case. Some of these features will remain. So you will always have integrals over, say, momentum or rapidity, and you have a wave factor with a momentum and an energy here. Like solutions of Maxwell's equations or any wave equation. And here you have something which is what we call the auxiliary function, 1 over 1 plus a, some generalization of the Fermi wave. And then in general you have some big thing here. And the integrals are coupled, not decoupled. This is the general structure. So in any case, we always first have to say, and it's for Bethe systems, it's better to work with rapidities rather than with momentum and energy. So the first thing is you have to describe the dispersion. So the momentum and energy as function of the rapidity. And so for the XX model, it's something very simple. The momentum is minus, in our conventions, minus I, log of minus I, hyperbolic tangents of lambda, and the energy is, you just have this derivative, which is 1 over cosh, something simple. Then there's the fundamental strip. Everything is in this rapidity variables. We're living on a cylinder. Everything is pi periodic. And then there's usually some, this is a critical model. So this is when you have a magnetic field characterized by the existence of Fermi points. Fermi points are the zeros or the roots of the energy. And in this fundamental strip, the function epsilon has precisely 2 zeros, which are the Fermi rapidities, lambda f plus minus, and the momentum evaluated on the Fermi rapidities is the Fermi momentum. So this is for the dispersion. Then I said there is some more stuff. The more stuff, if you know, for instance, form factors in quantum field theory, it may have some determinant structure. Or squares of determinants with some poles in here. This is such a thing. Here in this case it's a generalized Cauchy determinant, the square of a generalized Cauchy determinant, which has second order poles and particle and hole variables coincide. Then we have contours, particle and hole contours in the complex plane. So we have the strip minus, so the strip, fundamental strip is divided into 2 halves, and basically one contour goes around the lower half, there are the holes, and the other one around the upper half. So if you analyze the excitations of the quantum transfer matrix of the XX model, you can prove that they all lie on a closed curve here, and the magnetic field is lower than the critical field. And it's a discrete set with two accumulation points, two accumulation points of 0, 0, and 2. So in the vicinity of 0 and of pi 2, there are infinitely many roots, and everywhere else finitely many. And the excitations are particle-Hole excitations. So the dominant state has all black here, and then you take one beta root here, move it here, then create a hole here, and the particle. This is the picture. Okay, then there is something which is a finite temperature form of a shift function. Then two very mysterious things which give structure to everything, which are periodic Cauchy transforms of some combination of energy and the shift function. And then there is this double integral A, some amplitude. And now comes the formula. If you put all of this together, you get what you get. I mean, here all the limits are done. You get this form factor series. So it's for the transverse correlation function. It's not just product of two integrals, but for plus minus, you have different selection rules. You have one hole more than particles. So you have one hole, two holes, one particle, three holes, two particles. So it's an odd number of integrals here. The first term is a single integral, then 3, then 5, then 7. And the integrand is basically, again, such a wave factor, such a generalized, well, this now looks like a Bose function. It's a bit misleading because you have to think it together with the phi p, phi h function, and then this digit. And Fm is something explicit. If you're familiar with this model, at this point you will be amazed. There is some very well-known work from the early 90s of Goehmann, where they do the asymptotic analysis. And you will see that this is basically the leading part of the asymptotic analysis, and they have to extract it by doing split undetermined analysis. In our case, the series spits it out. It's a prefab. This is very nice. So this is now a series of classes of excitations, and it's something completely well defined. It's a piece now to study this is a piece of complex analysis. Yeah? So it's just a function to be further studied, and it is manifestly different from the series representation which was known before. And so we have studied this, and I could give several talks about it. It's I mean, this is just a series, but it's a series of multiple integrals, and you can spend time to understand the properties. I give you only one from one of the papers. So in this recent paper, we showed that in the space-like regime, so there's, if you remember the picture of which I showed you before, there were blue dots and red dots. Red dots were time-like and blue dots space-like regime, and here is also space-like and a time-like regime. And in the space-like regime, we could show that this form factor series is absolutely convergent and determines the long time large distance asymptotics in a very simple way. So here's the asymptotics, it's a constant term, this oscillating term, and then some exponentially decaying term. And we can estimate the corrections. They are exponentially small, decay faster than every polynomial, and we have an explicit and simple, nice expression for the constant term. This was not known before. So the asymptotic analysis of XXZ and Goehmann did not give this. Moreover, it was very hard for them because they had to analyze split-on determinants. Here, it comes from the series. And the amazing thing is that this can be analyzed by means of undergraduate analysis. So you need just Hadamard estimates for the determinants, and you can estimate a term by term in the multiple integral with some rather elementary relations. Short calculation. No higher asymptotic analysis is needed. So we were very happy with this. Okay, and here's the picture. Since this one is, we also can get a Fredholm determinant from that on which we did works. Those are the blue dots. So then you get everything numerically from the series. And the brown curve is the asymptotic formula. And of course, since the corrections are exponentially small, and here m is 100, so the corrections are the order e to minus some number times 100. That should be very good approximation. Okay. Now let me say something about the new stuff. The new stuff is beyond XX. So what is the problem? If data is not zero, the spectrum and the beta group patterns of the quantum transformatics are not sufficiently well understood. So I showed you this nice picture, the curve with the dots and so on. And in the general case, there may be wild patterns in the complex plane, and they are look more complicated than for the usual transformatics. This is the problem. Otherwise, we could do everything in full generality, but now we have to approach this more carefully. And one part of the spectrum which we understood well, and which is as simple as for the XX case, is the antiferromagnetic massive regime, so the regime which was studied by the Vertex operator approach by Goehmann. This one here, the white region in the lower right corner. In this region, and at low temperature, we have again a particle voltage. All strings disappear by some mysterious, I don't know, procedure, or I don't know how to call it. Anyway, there are no strings. I mean, this is not a mathematical theorem. For mathematicians, it's a conjecture, but it's a very strong conjecture, supported by numerics and by many. Well, there are some ways to construct strings, and you can just show that they fail. There will be no strings here, which are constructed the usual way, which doesn't mean that there may be other wired things. We cannot exclude that, but numerics makes it also very unlikely that there are these other wired things there. So very strong conjecture that there are no strings here, and that's why we can do all calculations. So let's again come back to the literature. As I said, Goehmann, using the ordinary transformatics, they got the form factors as multiple residues or multiple integrals. The form factors is the thing under the integral. We will have anyway a series of multiple integrals, but the integral itself is also a multiple integral. Then we did this analysis, ordinary transformatics using beta ansatz. So which meant we had to calculate these determinants which you have in beta ansatz in the Trotter limit, or in this case in the thermodynamic limit, including all string cases, which was hard work to analyze. This gives bad singularities, and we had to analyze all the singularities. We could do so, and what we got is we got multiple residues, and the functions of the multiple residues were Fredholm determinants. So even more complicated than this. Then in the static case, and also unpublished in the dynamical case, we did this for the quantum transformatics. And there the answer is we got Fredholm determinants. I mean, this 2016 work, this immediately generalizes to the dynamical case. And this is published work where we have Fredholm determinants. And now in our recent work, we got something where we have only finite determinants of simple functions, as I said, which I want to show you. And unfortunately, it takes now many slides to just introduce the functions to you and show you some formula. So you have to relax a little bit. It's like when I was a student, I was attending a seminar on philosophy about Hegel. And the professor was reading Hegel to us, and it's completely ununderstandable if somebody reads it to you. I will sit there, and he said, just relax. Listen. So just relax. So first of all, this is still preliminary. So instead of looking directly at the two-point functions, we look at the generating function, which is a bit simpler. So let us define, and I changed the notation in order to confuse you. So I know the eigenvalue ratio is excited state by dominant state I call rho. I do this, I change the notation in order to save space. So I denote the Robin's ratio of excited state by dominant state. And for the beta states, instead of psi n, I write nh prime. H prime is the magnetic field, and n is the nth excited state. And for the dominant state, I just write h. And I choose the magnetic field different for the dominant state and the excited state. So this is a control parameter, the difference in the magnetic fields, and I want to take derivatives with respect to that in order to get a correlation function. This is an old trick from 84, goes back to Zergin and Goehmann. So this is the generating function. The generating function is just, well, this is my thermal form factor series, as you see, and instead of this guy where you would have x and y, you have just this simple function, just only scalar products, no expectations, only scalar products. And here you have eigenvalue ratios. This is just the same as before, just in a new language. Instead of lambda over lambda, I write rho. And you have the amplitudes. Then, the amplitudes and the eigenvalue ratios will be related to the dispersion, to P and E, so momentum and energy. And here, the functions are a bit more complicated. Not just hyperbolic functions, but other functions will appear. And I first have to define the functions. The family of functions is still simple. The family of functions appearing here are Q-deformed gamma and Barnes functions. They were known by, I think, Barnes, maybe even earlier probably. I mean, they are special cases of Q hypergeometric functions, as I learned, introduced by Heine in 1846, so it's really classical analysis. There are many ways of introducing it. There's a whole family. The most elegant way would be to have a Q-Bohr-Muller theorem, which was only proved like 20 years ago, but it exists. But the easiest way is to first introduce Q multifactorials. So Q multifactorials is just multiple product with PQ parameters, and A is the variable. So these are Q factorials, infinite Q factorials. And then the gamma function is just basically 1 over Q to the xq with something, and the Barnes function is just has the product in the numerator and some integration. So some people don't like this. For instance, Jim O'Meara, they just use Q factorials, and it's maybe sometimes easier for immediate calculations, but the Q gamma and Q Barnes functions have the advantage that they satisfy very nice functional equations, like gamma, the same as gamma and Barnes function. Namely, well, first of all, there's normalization, but then you remember the gamma function. X times gamma of x is gamma of x plus 1, so here everything just gets a q. Instead of x, you have q number x, and for the Barnes function, you have the function. This is very useful for calculations, very, very useful. And the second thing is, if you write it like that, then the isotropic limit, which is very interesting from the physical point of view, the limit q to 1 is very easy. For q to 1, gamma q becomes gamma, q becomes g. That's what I like. And they are also related to theta functions. Theta function is like, well, 1 over theta 4 is square of two gamma cube functions. And the other theta functions are related to theta 4 by shifts. And this definition means, well, this is the deformed second functional equation of the gamma function. The second functional equation of the gamma function is pi over cosine pi gamma is gamma of 1/2 minus x pi over cosine pi gamma is gamma of 1/2 minus pi times 1/2 minus x times 1/2 plus x. And this is the Q version. Okay, so that's all. Now we can go to the physical functions. Momentum and energy. This is the dispersion relation in the massive antiferromagnetic regime. There is something which is called the dressed phase, so bare phase from beta ansatz dressed through linear integral equations, also expressed in terms of gamma q. Some people know this. This is related to the S matrix. Most people know the S matrix. If they know something of the XXZ model, then there are useful gamma functions. This goes back to Taftajan, Fadeev, something like that. Okay. And here is everything is uniform, and then there's what we call the shift function. The shift function is the sum over best phases, and this notation means I sum over all y in the set y and over all x in the set x. But if you have if mu is from y, we have a plus sign, and if mu is from x, we have a minus sign. This can be formalized by doing a degree map, but I don't want to explain this. I mean, it's just what I said. And also for products. For products, it's the logarithm. The minus gets in the denominator, the plus in the numerator. Okay. Then, this is what we learned in one of our old papers about the spectrum. What I said, there are no strings. All excitations of the quantum transfer matrix at low T and large enough Trotter number can be parameterized by even number of complex parameters inside some fundamental strip. Some strip is now of width gamma, and by a topological index K, and we call the parameters in the upper half-plane particles and the one in the lower half-plane holes, just as before. And for excited states, in our case, they're the ones which give non-zero matrix element. The cardinality of particle and whole sets must be the same. And up to corrections of order t to infinity, exponentially small. In the low t limit, there are these higher level beta equations. Determined by the shift function. Is the structure not so much different from the higher level beta ansatz equation for usual transformatics? But the quantum transfer matrix means something like big rotation. So in the usual transfer matrix, with the momentum here in the beta equations, the higher level here, you have the energy. Because you have interchange space and time direction. Very nice. So those are the curves. And this massive case means open curves. Here are the holes, and here are the particles. And this is already the critical case, which we are not considering. Closed curves in the critical case, open curves in the massive case. And they condense to these curves when t goes to 0. So, as I said, now we have to describe in our formula there were the amplitudes and the eigenvalue ratios. The eigenvalue ratios were known before in a nice way from our 2015 paper dedicated to Max's 75th birthday. So they are given just in terms of the momentum function, and there's this topological index k. And from that, you get all we needed is rho n at minus I gamma 2. This is the shift point to the power m. And this is this. And this limit can be also calculated. And the energy appears. Very nice. That's what we would expect. We would expect this wave factor. Momentum plus m times the distance times momentum plus time times energy. This appears here. Quite natural, but I would say, yeah, it's not obvious from the beginning in this case. Okay, now the amplitudes. For the amplitudes, we need more functions. Bare energy, difference of two cotangent functions. And we need something like, well, this is something like the root density function, which is here given in terms of ratios of theta function. Sigma 0 is something very simple. It's just basically up to some constant. It's the difference of a whole of, well, we sum up all particle roots and subtract all roots. And it's the average shift function. Then there are some weight functions, phi plus minus, again products of Q gamma functions. And finally we can define omega stands for the answer. The answer. Function omega. This is what I said, is just the functions of the function g, integral minus pi on 2, the weight, bare energy, and this function which is root density, or something like, is also similar to the rest energy function. And if you're familiar with the work of my friends Jimbo, Smirnov, Takayama, and some generalizations of this to finite temperature, which I was also involved, and there is also a function omega, there is this fermionic basis, and the omega function has such a structure. So this is the rate function, P function, bare energy. That's amazing. Similar structure appears here. There is a second one, omega bar, where just some minus signs are flipped. Okay, so then this generalized measure in the in our case, is just 1 over determinant of some auxiliary functions, which are solutions of nonlinear integral equations, which I won't show you. And finally, one more function, a function, which is, again, Barnes functions, gamma functions. Nobody can keep it in mind if I know so quickly, but I want to show you that there are just gamma functions and Barnes functions, some programs, and simple integrals. Oof, now there it is. This is the result for the amplitudes. So the amplitudes and the total limit are the measure which we need in order to transform sums into integrals. They will disappear after transforming sums into integrals in the zero temperature limit. It's like the Fermi measure, it will be 1 or 0. And then there is something simple, theta 2 squared of this difference of the sums of particles and holes, normalized by theta 2 squared. This function psi. This is very much like this generalized Cauchy determinant. And then the product of two determinants of all. That's it. If you open the book of Gilmour, you have a whole page of definitions for you have these multiple integrals, multiple residues. Here we have something simple. Note that the answer is explicit and defined entirely in terms of functions of the Q-gamma family. In particular, as opposed to previous results, there are no multiple integrals, no factor determinants involved. Last, we might think of the answer as a factorized form of the amplitudes. Instead of multiple integral, we have a determinant. The function omega remotely resembles the function little omega, appearing in the theta factorized static correlation functions, and taking the x limit is immediate. Just replace gamma q by gamma. Then we can insert this into the series, just transform using this measure sums into integrals, and then we get something which is not so much more complicated than sigma plus sigma minus series for the XX. So we have these factors. We have a product of two finite determinants of size L. L is the number of particles and holes. So in the one particle, one hole case, this is 1 by 1 determinant. Just two product of two functions, and so on. Something simple. And then we have to apply this operator. We do that, we get the two-point function. This is the new formula for the two-point function. It is minus 1 to the m times Baxter's square of Baxter's staggered polarization. And we have this is also very nice, if you like the technical detail. Applying this operator to the first term gives Baxter's staggered polarization square. It's very nice. It's a new derivation of this famous formula. And then there is this series. And as I said, this is simple enough for at least numerical evaluation of the first terms, and we hope that we will be able to use this in asymptotic analysis of the XXX case. So rather explicit, and I should, when we got this from the previous page, I used that these determinants at alpha equals u are 0. That's why the derivative acts only on this and on this. I mean, you take the derivative at 0 of a product of function, and two of them are 0 at this point. So this is this structure, and this we can prove directly, which was also a headache. And there we are. Summary and outlook. So we have devised the general part of the story, a thermal form factor series expansion for dynamical equation functions of fundamental integral lattice models. We have applied it to the transversal two-point function, the XX chain. The resulting series can be directly used for the long-time large-distance asymptotic analysis, and the correlation function at fixed t and in the space-like regime. We have applied our method to the longitudinal two-point function of the XXZ chain in the massive antiferromagnetic regime and in the low-t limit. This was the second part of the talk. And in this case, we have obtained expressions for the form factor amplitudes that contain only finite determinants, no infinite objects anymore. Future work extends this to the masses case. Well, this may be, I think, a month ago I would have said this is probably hopeless, but now I'm optimist. So let's try to extend this to the massless regime. And then we want to perform the long-time large distance analysis of the two-point function of the XXX chain. And completely different thing at the opposite side, this is low T. Maybe we would try high T. That's the next thing before we hopefully sometime get something in the general finite temperature case. Thank you very much for your attention.
Thank you, Frank. Very nice talk. Are there questions?
So you said you made a thermal form factor series. Can you just define one single thermal form factor? I mean, write a formula for a thermal form factor where you have some incoming state, outgoing state, and not the two-point function.
Well, this is a square of a form factor. This amplitude is a square of this amplitude. The point is, on the lattice, there is no natural normalization of a single form factor. That's why I always consider these amplitudes. So it's two form factors. Let's go back. The definition of A. I probably tried to show too much. So, see,
I see. Okay.
this is dominant state, excited state, and excited state, dominant state. The point is here the normalization. You would have to put square roots there if you really want to normalize it, and this is not natural for our calculation. So the true form factor would be h and h bar divided by square root of the denominator and the other one.
Yeah, but where is the operator? Don't you want to put some operator in between?
As I said, in this case, I use that if I, this I can explain to you. If I apply this derivative, derivative to this, it will create the operators. This is just, it's simple calculation. So
I understand.
Yeah. So there's the operator. The operator comes
by this trick. And then you put h to h bar, yes.
Yes. So this is actually, the main calculation is just of the calculation of this product of two form factors, if you wish. The rest is easy. I mean, so this is the hard work to get there. And then to put this in a series, this just, you can just do it. It takes an hour or two or so.
And can you express this thermal form factor in terms of the zero temperature form factor?
Yeah, there's, you mean the ones by Jimbo Weaver, right?
I guess when you put the temperature to...
Yes, there is a conjecture for that. We can, I mean, I have a conjecture how they are connected. Actually, they are not the same, but there's, the conjecture is actually rather simple. So if you take those and symmetrize them, you get the same as if you take the Jimbo Weaver ones and sum over all spin on quantum numbers. I mean, they have this epsilon prime, so plus minus. If you sum them up, and if you take ours and symmetrize in a specific way, I have to write it at the blackboard, what I mean by symmetrize. But basically, this is not symmetric in particle-hole parameters. So if you symmetrize, and they live on different contours, so you have to shift the contours and symmetrize the particle-hole parameters. Then we believe we get there. I can show you, we checked this numerically in our previous work for the, so this is particle-hole, so one particle-hole after symmetrizing gives the two-spin formula of Lasch-Kimmich. And I think now, so before we just had this conjecture and checked it numerically, but now I think we can prove it. Basically, I did the proof at the blackboard, and I just made a mistake, so it looks almost the same. There's some minus sign. It's just, as I said, I'm in the middle of this, and I'm rather confident that you will be able to do this for the two-spinel case. For the general case, it may be harder, because we will have to show that, what we have to show is that this product of the two determinants is related to the multiple integral. There's a way of, I can imagine how this can happen. There is an integral inside the determinant. If you deform the I have some ideas about that.
Maybe we are getting a bit technical.
We
can discuss this.
I can tell you. So we have some ideas, but it is not so clear. Now we are studying these functions. And Konstantin is very much involved in that, who's sitting behind you. He's, so one way is, you can make this also explicit in terms of these Q hypergeometric series. In a sense, it's the most obvious way to look at that. If you do that, actually that's why I said we can probably prove it for L equal 1. For L equal 1, we can do the manipulations of the series using some calculus of this Q hypergeometric series. There are many formula. Just learning about this, and then you can write this product. It will be just some theta functions. And then if you symmetrize, then we should get Lashkev's result here. I'm sure. And in the modular case, I'm not so sure. We'll see. The paper is not written, we are just in the process of doing that.
Okay. Other questions? I have one, maybe naive. So this is for the longitudinal two-point function.
Yes.
Do you think that you can do it for the plus minus?
Yes.
You can do.
Yes. There is no.
Even in XXZ.
Yeah, in XXZ for the plus minus is also possible. There is I didn't tell you how I did it, but the main point here is not connected with the operator. So we can also do it for the plus minus functions. There will be some complications, but the complications will be in this part. In fact, it's maybe the function there. I would actually guess that we have maybe determinants where one row of the matrix is modified. This is very typical for the plus-minus case. Well, that's all. It's more technical. Typically, it's harder to do. It takes twice as long calculations. But we could also do this with the Vetter determinants. We could also do the plus-minus case. It was more technical, took longer, with less fun then. But I believe, yes, it's not. I think it's the main point here is that the Vetter determinants are not gone. What we transform them in a way that we have Vetter determinants determinant of identity plus some integral operator, and we extract some stuff such that the integral operator, the kernel of the integral operator, has the property that it goes exponentially to 0 with temperature. So the 0 temperature limit, the Vetter determinants are just 1. So this core part will be the same for the plus-minus equation. So I believe we didn't do it, we didn't start, but yes. A different thing and more hard will be the massless. The massless case. For the massless case, I have just some, from the last 2 weeks or so, some very recent new ideas that make me believe that there is a chance, but I wouldn't bet my house on that. I'm not sure. Corinthian always asked me, would you be ready to be burned for that? And the answer had to be yes.
Okay. So thank you. Let's thank the speaker again. So it's coffee break upstairs.